All right. A few months back, I was surfing YouTube and came across Tim K50HY out of Midland, Texas here, and he had a great three-part series on infant half waves, and it was very informative. It wasn't too far over my head. It was very nice to understand, and I was like, "Wow, this is pretty cool." I think other people could get a um, enjoy some of the talk that he was presenting, and I think what that I really liked about it is, at least for me and maybe other people, when they're new, the first thing they're taught is SWR, SWR, SWR. And it's not always just about the SWR, it's about other things that can make the antenna much more efficient. And Tim was highlighting a lot of that. So, Tim, thank you very much for joining us. And let me throw it over to you, and it's all yours.
Okay, well, first of all, thank you all for inviting me to speak. I'm hoping this will be both interesting and informative. Let me see if I can share my screen here. Uh, and get that out of the way. Okay, can everybody see the screen now? And can you hear me? Okay, I'm
And
guessing you can hear
we
me.
got you. You're coming in.
Okay, perfect, perfect. Okay, so first of all, a little bit about myself. Let's see if I can get this to go. I was first licensed at the age of 13 in the mid 90s. Of course, that was a Tech Plus license. And you still had the code requirement. And I didn't really have any interest in Morse code, but going through the process of learning CW, that became my primary interest in the hobby and has remained my primary interest in the hobby. Although maybe I'll get into Air Mobile now or the Parachute Mobile. That sounds interesting. Um, so I returned. I had a really long period where I was just kind of lost interest in ham radio, and I returned in 2024. I had to retake my test. My license had expired, and then I quickly upgraded to an extra. I had my general before. What got me back into the hobby was looking at all the portable operators doing parks on the air, summits on the air. And that just looked really interesting to me. And of course, with my background at CW as a kid, I kind of wanted to relearn that. So that got me back in the hobby. And I've been experimenting with just a lot of different antennas. That was one thing I really liked about going out to the parks. I could set up different antennas and try different things and kind of learning a lot along the way. And eventually I started posting a couple videos on YouTube. I have a very small YouTube channel, nothing fancy, but it is a lot of fun. I've learned a lot along the way. Now, outside of radio, I work as a nurse anesthetist. I primarily practice obstetrical anesthesia now, but I've practiced a lot of different types of anesthesia in the past. I've been a CRNA for about 13 years. I ran across this quote the other day, and I thought it was kind of interesting and pertained to this topic. What I cannot create, I do not understand by Richard Feynman. And I thought that was especially interesting when it came to antennas because I started building antennas. I had no idea what I was doing at first. But once I started building them, I started to understand how they work. And I think that's probably one of the most fascinating parts about this hobby to me is you can cut a simple piece of wire and start talking to people all over the world. And that's just always been a lot of fun for me. So a little bit about what we're going to cover. Now, this is mostly going to be from a practical point of view. I'm not going to get into deep theory, anything like that. First of all, I can't because I don't have the knowledge. And second of all, you can really get in the weeds with this stuff. The more I learn about the antennas, the more I realize how deep of a topic it is and how complicated it can get. So we're going to talk about the basics of an infrared half wave. We'll talk about the feed point impedance, impedance transformers like 49 to 1 and 64 to 1. We'll talk about whether or not you need a counterpoise. And then we'll talk about all the different ways you can deploy the antenna. And we'll use computer modeling to kind of get an idea about the radiation patterns. And then we'll talk about the performance of the antenna. And of course, the downsides of the trade-offs. I'm not here to tell you that the in-fed half wave is the best antenna in the world. It's not. It's a compromised antenna, but it's a tool in the toolbox. And I think if you understand how it works, you can really maximize your results with it. And I've had a lot of really good luck with this antenna over the last couple of years. Now, first of all, the infed half wave is extremely popular now, and there's a variety of reasons for that. First of all, it's very simple. It's one radiating wire, which makes it very easy to deploy, especially when you're out portable. But it's also a very convenient antenna if you live in a homeowners association like myself. You can hide the feed point and the impedance transformer behind a fence or somewhere and throw a wire up in a tree. And now you can get on HF. And so it's a very convenient antenna if you live in an HOA. Essentially, all it is a half wavelength piece of wire that you feed at the end. And because of that, your feed point impedance is going to be quite high. And we'll talk about that in the next slide. And so that leads to using some way to match that impedance to 50 ohms, either impedance transformer, LC network. There's a lot of different ways to do it, but most commonly an impedance transformer, like a 49 to 1 or 56 to 1. Now, because we're feeding this antenna at the end, you not only get the band that it is cut for, but you also get all the harmonics. So that's quite a bit different than a dipole, which is typically a monoband antenna. Infed half wave will work on the primary band. So for example, if you have a 40-meter infed half wave that's approximately 66 feet, it'll work on 40 meters, 20 meters, 15, and 10 meters without a tuner. You can cut a longer infed half wave and like an 80-meter infed half wave and cover most of the HF bands. This is a little diagram I made for one of my videos. And as you can see, the black line represents just a half wavelength piece of wire, and you've got different feed points. So here in the middle, if you feed a half wavelength piece of wire in the middle, it's a dipole or even a quarter wave vertical. And the impedance is going to be close enough to 50 ohms where you don't need any type of matching unit, between 50 and 75 ohms. Now, a lot of times you're going to use a one-to-one balun, but the impedance is close enough that you can direct feed it. And then the blue line and the red line represent current on the blue line and voltage on the red line. So a dipole current is at the maximum at the feed point and voltage at the minimum. Now, when we start moving the feed point to one side or the other, now our impedance is going to start to rise. So an off-center fed dipole has an impedance somewhere around 200 ohms. And if you take 200 ohms, divide that by 50 ohms is what your coax and radio are expecting, you get 4. So you use a 4-to-1 unin or balun, and that's going to drop your feed point impedance to 50 ohms. And then if you go further down, you've got something like a non-resonant wire, which has a varying feed point impedance. But if you take 450 ohms divided by 50, you're going to get 9. So sometimes with the infed random wire, you're going to use a 9-to-1, which will bring the feed point impedance down far enough to where your internal tuner can match that antenna. And then finally, what we're talking about today is the infed half wave. We're feeding the antenna at the end of this half wavelength piece of wire. Now our feed point impedance is very high, a couple thousand ohms. So if you take 2,450 ohms divided by 50, you're going to get 49. So that's where you're going to use a 49-to-1 on it. Now, the other thing to note is now our current is at a minimum and our voltage is at a maximum. So this is often called a voltage fed antenna, where a dipole would be a current fed antenna. And one thing to note here, with say a quarter wave vertical, that's why you really need a really good ground plane, because the current is at a maximum of that feed point. And so if you have a ground mounted vertical, you really need a lot of ground radials because of all that current at the feed point, which is completely different for the infed half wave. Our current's at the minimum. And we'll see, we'll talk about counterpoise here in a couple slides. Now, when we talk about impedance transformers, here's a simple schematic of a 49-to-1. You've got your low impedance side on the left, the high impedance side on the right, and you have two windings. You have a primary winding and a secondary winding, and you'll also notice a capacitor here. Now, the capacitor is used Basically to help get a better SWR on the higher frequencies. It basically helps out with some stray inductance, and it will help you get a better SWR on 10 meters in particular. Now, on the left side is a very typical way to wind one of these 49 to 1s. You see that it has 2 primary turns, 14 secondary turns. So you start here on the ground and you have your primary and secondary. This is a twisted primary. So it's basically twisted around the secondary. And after 2 turns, the primary comes out to the center connector of the your center connector. And then you've got the capacitor across the ground and the center connector. And then you have the rest of your 14 turns. This one has a crossover. And then on the right side is a different way to wind these. This is called an auto transformer. And what you'll notice here is you've got the secondary started at the ground side, and then you've got after 2 turns, it's tapped, and that's your primary going to the center connector of your coax. And then you have the rest of your 14 turns. And there's a couple advantages to the auto transformer. First of all, I find them easier to wind because you don't need to make the twisted primary. You simply just tap it. But it also may have some benefits and efficiency, which we'll look at here in a little bit. Now, let's talk a little bit about what makes certain transformers and the impedance ratio. And it really has to do with the turn ratio between the primary and the secondary winding. So we said that a 49 to 1 has 2 primary, 14 secondary. If you simplify that, you get your turn ratio of 7 to 1. And if you square that, that's going to give you your impedance ratio. So 7 to 1 turn ratio squared is going to be 49 to 1, and that's going to be your impedance transformation. And that works for all the other types of transformers as well. So a 4 to 1 Unin, which I've made a few of, often have 8 primary, 16 secondary. So you simplify that, that's 2 to 1 turn ratio, which gives you a 4 to 1 impedance ratio. Let's say you add another turn to your secondary, so you have 2 primary and 15 secondary. If you simplify that, that's 7 to 1 turn ratio squared. That's your 56 to 1. So that just kind of gives you an idea of how those transformers work. Now, this is the biggest complaint or the biggest issue with a end-fed half wave, and it's really efficiency. There is loss in almost every part of your antenna system, but a 49 to 1 Unin typically has quite a bit of loss associated with it. A typical 49 to 1 is has about 20 to 30% loss. So if you're transmitting 100 watts, you could be only radiating 70 to 80 watts or less. And I kind of discovered this by accident. I was using end-fed half wave, and after about an hour or so, I go to pack up after a Parks on the Air activation. I noticed my transformer was just really hot. I mean, melting through the enclosure. And so, to me, I'm thinking, why is it getting so hot? There must be some loss. And sure enough, I did some research and found out that there is quite a bit of loss associated with the transformer. But then I did some more research and discovered that that really depends on the type of core, the winding, and the frequency. And I eventually found Colin MM0OPX and his YouTube channel. You might have seen it. He's done an extensive amount of testing on different types of winding, toroids, all different types of testing. And he's come up with some pretty efficient end-fed half-wave transformers. And so I decided to build one and do some testing. And the way that he tests the efficiency is using this method here. This is when I tested my 49 to 1. And so what you can do, this is called the back-to-back method. And you can wind 2 identical transformers and hook them together. And then you can send a signal out of the S11 port of your Nano VNA, and that will go through one transformer and then bring up the impedance and then go through another transformer that'll bring it back down. And then you can measure the loss on this port. And you can divide that by 2, plug it into a formula, and that will give you your percentage efficiency. Now, this is not a real world efficiency. The criticism with this is the nano VNA uses a very tiny amount of power. So things change quite a bit when you add, real RF, real power, and you have heat and reactance and all these things. But this is the only way I know to test the efficiency of these transformers. And you can kind of maximize the efficiency and hopefully maximize the efficiency of the antenna by making a more efficient transformer. I'm not sure what the actual loss is when you get out to the field, but maximizing, the efficiency of the transformer is definitely going to help. Now, here is another slide about transformers. Here on the left are the transformers that I've built. And as you can see, I use Colin MM0OPX's recommendation on this toroid. It's listed down here. And if anybody has any questions about this, they can contact me afterwards and I can link them. You can get these on DigiKey. They're about $8. So as you notice, it's a really thick toroid compared to something like an FT240-43, which is a very common toroid for 49 to 1s. But what this does is it gives you a more efficient transformer. It also can handle more power. This toroid can handle 100 watts digital. I've run 100 watts CW through this thing all day and it barely gets warm. And then, of course, they have a smaller version of a very similar toroid that I've used for QRP work. In fact, I use this exact impedance transformer for a SOTA activation on this past Tuesday, and it worked really, really well. Of course, I was at 8,000 feet. Anything works pretty well at that height. Here is just my spreadsheet of my efficiency readings of this transformer. And you can see that using the back-to-back method on 20 meters, I was getting about 91% efficiency. It goes down a little bit on 10 meters, 87%, and then 90% down on 80 meters, but still quite a bit better than some of the other transformers. Now, you can easily buy a commercial end-fed half-wave. In fact, almost everybody these days seems to be selling their own version of an end-fed half-wave. I think that's primarily because they're so easy to make and fairly inexpensive. You can build one of these for $10 to $20 depending on what materials you have on hand. But you can also purchase a pre-built one. This is a 1010. I've used these in the past. In fact, this is the one I still use at home. You can see that the efficiency is a little bit less, 80%. And this is the My Antennas 56 to 1, and it has a fairly good efficiency of 91%. However, it is more expensive. Now, once you have your transformer, you're going to have to cut some wire. And of course, you can use the formula that we all learned when we took our technician test. 468 divided by frequency in megahertz is going to give you a half wavelength in feet. And you really just have to decide what bands you're going to want to cover. I tend to operate 40 meters through 10 meters simply because I'm usually operating portable or here at my house where I don't have a whole lot of room. But if you have more room, you can cut an 80-meter end-fed half wave and get most of the HF bands. Some of them may require a tuner, but you can get on the air with just one piece of wire, and it works very well. My recommendation is to cut the wire long, and then you can trim it or fold it back to get the resonant portion where you want by using an antenna analyzer. Now, counterpoise. This is a very debated topic online. You'll see people saying you do not need a counterpoise with an end-fed half wave. I've been using this antenna for many years. I never use a counterpoise, and it works great. Well, that's not necessarily true. You do need a counterpoise. However, it's typically recommended just 5% of a wavelength because there still is a small amount of return current on an end-fed half wave. So for a 20-meter end-fed half wave, you'll need something like a 3-foot counterpoise, or for a 40-meter, about 6.5 feet. And of course, double that for 80 meters. Now, a lot of people don't use a counterpoise, and at that point, their coax shield is acting as a counterpoise. And some people actually put a choke, 5% of a wavelength of the lowest frequency they're going to use, on the coax. But for me, I tend to use a choke at the feed point and have a dedicated counterpoise. I feel like that is a little bit more elegant way to do it. And there's a couple advantages. First of all, it's going to keep common mode current off of your feed line and RF out of the shack. When I first started doing a lot of portable operations, I never used a choke. And occasionally I would get RF burns from my key because I was getting a lot of common mode current or RF back on my radio. And using a choke pretty much stopped that. The other thing is it may help you get more consistent SWR curves. If you're using your coax as the counterpoise, every time you deploy this antenna, you may have varying SWR curves and it may shift. I find that using a choke and a dedicated counterpoise keeps things pretty consistent with each use. One thing that was kind of surprising to me is using a choke at the feed point can really help reduce RFI on the feed line. Here at my house, I've had an in-fed half wave since I got my license back for a couple of years. I didn't use it a whole lot because it was an extremely noisy antenna. My signal was getting out fine, but I can't hear people that well. I finally got around to putting a choke at the feed point. I could not believe how much that reduced the noise, especially on 20 meters. It made the antenna much more usable for me. So placing a choke at the feed point is something that I pretty much always do. I think it's a good practice, but you can get away without it. It's not, I'm not saying you have to. It's just, I think it works a little better. This is a simple diagram of an end-fed half wave. You got a half wave length piece of wire going to your impedance transformer. Get your counterpoise. Of course, you can use your coax as a counterpoise. I've got a choke at the feed point and then the feed line going to the radio. Now, if you're lucky, you can connect this antenna up and you're going to get some nice SWR dips at the portions of the band that you're going to want to operate. This is my end-fed half wave at home. I got lucky on it. I have really nice dips in the CW portion of 40, 20, 15, and 10. Now, like Rob said earlier, SWR does not mean you have a good antenna. You can have a one-to-one SWR. That's simply a measure of how well the antenna is matched to the feed line. Now, it does help out because you don't have to use a tuner and your radio is happy, but it doesn't mean you have an efficient radiating antenna. And you know what a lot of people will say in the comments on a lot of stuff. Well, a dummy load has a one-to-one, but it's a poor radiator. But I think a better example is, say, if I use a quarter wave vertical in my soil out here in West Texas, which is the desert, and I have, just a couple ground radials, I could have, 40, 50% loss due to ground loss. And that's a little bit better representation. I could have a perfect one-to-one SWR, but I have all this loss on the antenna, or you could have a very poor radiator. So SWR is not everything. It's very helpful to have a low SWR for your radio, but it doesn't mean you have an efficient antenna. One of my favorite antennas is a non-resident antenna, a doublet, which has a very high SWR, but because we're feeding it with ladder line, it has very low loss and it's a very efficient radiator. Now, every once in a while, when you build one of these end-fed half waves, you're going to have something like this happen. And I don't know how well you can see this, but you can see that the SWR dip on 40 meters is right in the CW portion. And then with each band, it starts going higher and higher. And by the time you get to 10 meters, it's fairly high in the band. If I want to operate CW, my SWR is now 3-to-1. And this can be even worse on, say, an 80-meter end-fed half wave. Sometimes lining up the SWR dips is a little bit of a challenge. So there's a couple tricks to help out with that. The first is a compensation coil. This is simply placing a coil about 6 feet up on the radiating wire. And what this does is help fine tune the harmonics. So you're placing basically some inductance, and that's going to lower the resonant frequency on the higher bands. So placing this coil on that previous antenna should lower the resonant frequencies on both 15 meters and 10 meters, and it shouldn't really affect 40 meters that much. And you can simply accomplish this by making a coil 5 to 8 turns on a 1 to 1.25 inch form, like a PVC pipe or a 3D printed form, whatever you have. And that tends to work fairly well. I ran across another method recently, and I haven't personally tried this, but it looked really interesting. And I saw a lecture, and I can forward someone to that lecture if they contact me after this. But he used a capacitor. So it's basically kind of using the opposite. You're using some capacitance, about 30–40% up the wire. And what this does, in my understanding, is raise the lower band's resonant frequency up instead of bringing the higher frequencies down. So that's just another way to do it. But what you'll notice here on this picture is he's also got a resistor. He's got a 33K resistor, and that's just to bleed off the static. So that's basically wired in parallel with the capacitor. I believe the static buildup on the antenna can ruin the capacitor, and that's why he put that there. Now, this is the most interesting part of this antenna to me, and this is kind of what got me using the infrared half wave more. I started doing some very simple antenna modeling. And so we're going to look at some radiation patterns of a few of the different configurations. The one great thing about this antenna is you can deploy it in a bunch of different ways: horizontal, vertical, sloper, inverted V, inverted L, and there are many others, but these are the ones we're going to look at. But the most interesting thing is the radiation patterns change not only with each configuration, but with each harmonic. So each band, the radiation pattern is going to slightly change. And so I was kind of interested in researching this just to figure out how I want to deploy this antenna. Now, one thing about computer modeling, I'm still very new to it, but there's a lot of ways to manipulate the computer models. You can use really good soil that's going to give you better figures on your antenna, lower takeoff angle, more gain. You can model it over salt water. You can raise the height of the antenna. What I'm really interested in is kind of real world scenarios. So I've modeled all these on poor to average soil with reasonable heights as well. Now, every once in a while, you might hear someone refer to an end-fed half wave as an end-fed dipole, and that kind of confused me at first. But then I started looking into it. If you deploy an end-fed half wave in the same way you would deploy a dipole, like up half a wavelength horizontally, you get essentially the same radiation pattern. And that's because the current distribution along the wire is the same regardless of where you feed it. So if you deploy them in similar manners, you're going to get similar radiation patterns. So this is a end-fed half wave, 20-meter end-fed half wave deployed a half wavelength above the ground. And you can see our very standard broadside dipole radiation pattern with some really nice gain. Most people probably wouldn't deploy it this way unless you really just can't get away with feeding something in the middle. But it is a very nice way to deploy these if you can. Next, we'll look at a vertical end-fed half wave. And this is a very popular way to deploy this antenna. Now, most people cannot deploy a 40-meter vertical end-fed half wave. 66 vertical foot wire. But I did have someone comment on my video and says that he has some 70-foot trees in his backyard, and he has one and said it is absolutely wonderful for DX on 40 meters. And I can see why. There's a couple advantages of a half wavelength vertical over a quarter wavelength. First of all, you get a little bit more gain and a lower takeoff angle. So a half wave vertical, you're looking at, this is a 20-meter half wave vertical. You get a takeoff angle of 18 degrees and you get gain of about 0.8 dBi. If you compare that to a quarter wave vertical has about 0 dBi of gain at 24 degrees. So, and it looks a little bit better at lower angles. At 5 degrees, you're a couple dB better. So for DX, a half wave vertical might be a little bit better. Now, a 20-meter end-fed half wave will also work on 10 meters. But you can see here the radiation pattern is not the most useful if you're looking to get DX. It's a very high angle. So I kind of recommend, if you're going to do a vertical end-fed half wave, to use it as a monoband antenna. This right here is the way I deploy a vertical end-fed half wave quite a bit. And you can see it's just a PVC pipe with my 49:1, and I've got a 25-foot whip here. And I can adjust this and be resonant from 17 meters to 10 meters. It's not quite long enough for 20 meters. I have another piece of wire that I cut for a vertical 20-meter infant half wave. One other thing to note is one other advantage of using this as a vertical, you don't need an extensive ground plane like you need with a quarter wave vertical. You just need that little counterpoise. For me, it's a little quicker antenna to deploy. You don't have to put a bunch of ground radials. If I do use a quarter wave vertical, I tend to use elevated radials. That's another topic, but more efficient that way, and you need less of them. Now, the sloper is probably the most common way people deploy these. You can see here is my model. I've got the feed point about 3 feet up, and then the end of the wire is about 30 feet up. Now, I'm not going to talk about 40 meters too much. Now, all these models are pretty much a 40-meter infed half wave. On the lower bands, you really can't get this antenna high enough to get lower angle gain. So it's going to be an NVIS antenna on 40 meters for pretty much every configuration. So you get mostly high angle gain, great for regional context, but not so great for long distance. On 20 meters, a sloper has developed 2 lobes, as you can see here. It's a full wavelength. And you get this main horseshoe-shaped lobe off the end of the wire. And this right here is the elevation plot. And as you can see, we're getting about 4.5 dBi gain at 40 degrees. So it's fairly high. And at 5 degrees off the horizon, it's about negative 6.3 dBi. And the reason we talk about 5 degrees off the horizon, most of your DX is going to come about 5 to 10 degrees off the horizon, so down in this area. And it's kind of hard to get gain from your antennas at this angle. So a lot of times people compare antennas using that metric to compare how well of a DX antenna is. So the sloper on 20 meters may not be a great DX antenna, but it's probably going to work really good for something like POTA because you may be trying to get contacts a few states over or just here in the US, and I think that's going to work pretty well. Now, 15 meters, it starts to get a little more interesting because we start developing more lobes. This is the sloper, and we're looking down. So this is the azimuth plot, and the wire is in the y-axis here, so going in this direction. And you'll notice 2 main lobes here off the about 45 degrees off the end of the sloper. And you also get a little bit of a lobe in the back as well. But this is a look at that main lobe. And so now we're starting to get some pretty good gain at lower angles, 5.4 dBi at 24 degrees. And now we're at negative 2.3 dBi at 5 degrees. So fairly decent for DX if conditions are, if the band's open, of course. So now on 10 meters, it's very similar. We're getting 5.8 dBi at 18 degrees now. And then it's right at 0 dBi at 5 degrees. So if you compare that to a quarter wave vertical, you're up about 5 or 6 dB at 5 degrees off the horizon. So probably a much better DX antenna than, say, just a simple quarter wave vertical. Now, the inverted V is kind of interesting. Here you can see I've got the feed point up 3 feet. It's going up 30 feet in the middle, and then it goes down on the other side. And we're getting some really nice broadside gain on 20 meters. Now, again, on 40 meters, it's pretty much the same as we saw before in NVIS antenna. But on 20 meters, we get some really nice broadside gain. And it's about 3.4 dBi at 18 degrees, and it's negative 2 dBi at 5 degrees. So it looks pretty interesting on 20 meters, but the problem comes on 15 meters. We get this kind of wonky shaped radiation pattern with a lot of high angle radiation and not much low angle. So the inverted V doesn't look like a great antenna to me for 15 meters, especially if you're targeting DX. For me, most of my DX comes when I'm out operating portable on 10 and 15 meters. So for 15 meters, I probably wouldn't use this, but if I was just going to do a 20-meter activation, I think it'd work really well. But on 10 meters, we do get some lower angle gain. These 2 lobes off the end of the inverted V, so it'll be off this end of the inverted V, we get about 4.2 dBi at 11 degrees, so fairly low angle, but a lot of high angle radiation as well. And then the final configuration we're going to talk about is the inverted L. So this is the feed point up about 3 feet, going up 30 feet, and then a horizontal section for the rest of the antenna. Now, the 40 meter in this antenna of 40 meters does look a slight bit better than the other configuration. I think because we have this vertical section, it's basically the Invis style antenna squashed down a little bit. You get a little bit lower angle gain off the side, but I'm not showing you that here, but a little bit better, but not really. I don't think you'd really notice it a whole lot. But on 20 meters, we're getting some really nice broadside gain to the horizontal portion of the inverted L. It's 4.7 dBi at 26 degrees and negative 3.8 dBi at 5 degrees. But on 15 meters, this starts looking really interesting. We get this clover leaf shaped pattern, and about 45 degrees off the end of the horizontal section of the wire, we get these two lobes. And this is a cross section of one of those lobes. We're getting 6.1 dBi at 21 degrees, and now we're at negative 1.6 at 5 degrees. So fairly good for DX. And again, on 10 meters, it's very similar. We get these nice lobes, 45 degrees off the end of the wire. And now we're getting, I think, around 5 dBi of gain at 18 degrees and negative 1.6 at 5 degrees. So after looking at all the radiation patterns, I tend to use an inverted L when I use this antenna. To me, it has the most useful radiation patterns, especially if you're trying to get DX. But now you have to decide how you want to deploy the antenna. So the best way to do that is to go on a website. I forget the name of this website, but you can plug in your grid square, and it'll give you an azimuth map. And this shows you, where all your DX contacts are in proximity to you, what degrees or where you need to point the antenna. Naively, when I got back in the hobby, I looked at a globe and I'm thinking Europe is somewhere straight east of me, and that's just not the case. It's almost straight north, or just kind of 40 degrees. And then I have Japan off the other side at about 315, 320 degrees. So I typically deploy this antenna facing straight north. On 20 meters, I get really nice broadside gain, which covers the whole US. Now, I will have some knolls directly north of me and probably south of me, but I get really good coverage of the whole US. But on 15 and 10 meters, now I'm getting those lobes that have really low angle gain going towards Europe, and then also going towards Japan and possibly Australia. So really good for DX. Early in the morning, I tend to get a lot of DX into Europe, and then late in the afternoon, possibly get DX into Japan. And of course, that all depends on band conditions, which we know the solar cycle has been kind of crazy with a lot of flares and stuff. But this antenna has worked really well for me. This is just a picture of a deployment that I had. This is a 30-foot mast. I've got the antenna going up. You can see it's blowing over. I've got the West Texas wind blowing that over quite a bit. And that goes to another mast. Now, most of the time, I won't go through the effort of putting a second mast. I'll have a lazy inverted L. So I'll just connect like 50 feet of paracord to the end here and just have it sloping down. I'll still have the end of the wire 15, 20 feet up, and that works out fairly well. Now, what I'm really interested in is trying to, objectively determine how well this antenna is working, and all my antennas really. And there's a couple ways to do that. Now, there's a lot of subjective data. You can say, well, I made contacts all over Europe. I had the station contact me in Germany. My antenna is working well. However, that's not necessarily the case, especially for parks in the air, some side of the air. a lot of times the DX station is doing most of the work. They have a much better station with high gain antennas, really good quiet receive antennas, and they can work the world pretty much whenever they want. What I'm really interested in is objective data. Is my signal actually getting where I want it to get? And so I use two methods. First, the Kiwi SDR, which is kind of time consuming. You can pull up a Kiwi SDR and pick a station with low noise and compare different antennas. There's actually an S meter attachment, and that will give you a very accurate signal strength. And so you can compare different antennas. And I've done that in some of my videos, but it's fairly common, fairly time consuming. What I prefer to use is the reverse beacon network. As a CW operator, this is an invaluable resource. If you're not familiar with the reverse beacon network, it's there are stations all over the world that basically listen to CW and decode it. And they post on a website and give you a signal to noise ratio of where your signal is being heard. And so, after each activation, I can go and look, hey, where's my signal being heard? Is my signal even getting out? Sometimes at a park and I'm not getting any contacts, and I'll look at the reverse beacon network, and sure enough, that band is just not open. I'll be on 10 meters calling CQ for 10 minutes, not make a single contact. But I actually wrote a website or put together a website that gives you a visual representation of the signal noise ratio. So this is an in-fed half wave on a few different bands after an activation. So right here, you can see this activation, 10 meters was open, and my in-fed half wave was getting into Europe quite well. My signal noise ratio was, up above 20 dB in a lot of these stations. And, I was actually working, QRP stations in Europe when 10 meters is open. And so that's when the antenna is working very well. Now, 15 meters, you can see that my signal didn't quite make it over the pond, but I did have some very nice signal noise ratio across the entire US. And you can kind of see the radiation patterns tend to be in the direction of the models. So that kind of is interesting to look at. And then the subjective data is the QSOs. This is one activation I did with my in-fed half wave. This is the video I put together. In the last video of that series, I go out, set up the antenna, and make some contacts. And you can see I made a fair amount of DX. Now, 10 meters was really quite good that day, and it did fairly well. And then here is the map. You can see the green dots are 20 meters, and I made a lot of contacts all across the US. But most of my contacts on 10 meters were in the direction of the lobes from the radiation pattern. You can see I even had one down here in South America. If you remember, there were some weaker lobes about 45 degrees off the backside of that inverted L. So the models seem to reflect real world use. And finally, you can get pretty creative with some of these antennas. My good friend now, Greg KJ6ER, has a new antenna design that I've been using recently, and that uses an in-fed half wave for the radiating element, but it also has a reflector element. So this is a two-element antenna, and it's basically a vertical Moxon. It has a in-fed half wave and an inverted L with an insulator here, and then a reflector in an L shape. And this antenna, it works fantastic. It has a really nice broadside, a really nice broad radiation pattern. And also look at the elevation plot here. You get some really nice gain up higher, but also at 5 degrees off the horizon, it's about 0 dBi. And I find that this antenna works extremely well for something like parks in the air, because you're just basically sending out a wide, broad bubble of RF. So there's a lot of different ways you can use an in-fed half wave. And I think that, if you kind of understand the radiation patterns and how it works, and you can optimize your efficiency of your transformer, it can be a very effective antenna. And I think it's definitely an antenna that anybody should have in their toolbox. With that, hopefully I didn't talk too quickly. I was trying not to take up too much time. If there are any questions, I'll feel free to, I'll try to answer them.
Yeah, so this is how we're going to do it real quick, everybody. You can unshare now if you want.
Okay.
It's up to you unless you've got more data, and I'll take the lights in the back so I'm not completely in the dark. Okay, so I did see some people on Zoom, by the way, that they were doing it right. If they have questions, go ahead and put them up there, and we'll get all those questions. And then what I'll do is I'll take questions in the room here first. Just so you know, Tim, we have about 45 in the room, and you had what, a dozen or so on Zoom. So you had quite a nice audience tonight.
Well,
25. There you go. Okay, I got everybody. Hang on, hang on. We'll get you, Tim. One of the questions that come up is your PowerPoint available? And we do archive our Zoom presentations on
okay.
our website. So if you just want to send that PowerPoint to me, you've got my email already. We'll make sure it
Yes,
gets
sir.
into our archive. So hopefully that will satisfy everybody's question there. So
Sure. Be happy to do that.
with that being said, I'm going to start on this side, then we'll go to this side. So I see Andy's hand. So we'll go to Andy first. All right, this Andy.
Well, I'm an old ham, and in the old days, I used a pi tank circuit. Have you
Uh-huh.
used a pi tank at all instead of a transformer? I wonder if it's more efficient.
Yes, I haven't, but I have looked into that. And there's a lot of ways to match this antenna that are probably more efficient than an impedance transformer. I think that impedance transformer is probably the most convenient way to do it and probably the easiest. For example, I just got a simple MFJ tiny little L network tuner. And I think that might actually work. And I believe there's less loss associated if you use other types of matching networks, especially if you're going to use a monoband version. I don't know how well that will work. You may have to retune it with each band. And I think that's why an impedance transformer is typically used, because you can basically use it on all the bands without having to adjust anything.
All right, thank you. All right, got another question over here. One moment. Oh, Daryl's up. Daryl's up. Then we'll get you here. Nope.
Okay, thanks. Hey, great presentation. Thank you very much. One question, I thought the reflector concept was pretty cool. Now I'm in the back of the room and I couldn't really see how you had it configured, but I presume the driven element is essentially, you start at 3 feet, go up 30 feet, go across, and then the reflector, is it just kind of opposite of that? And of
So
course, the reflector is not connected electrically, right?
yeah, correct. It's not. So this is actually tuned as a monoband antenna, and it looks kind of complicated. And there's a great document that I can share with you, and that's put out by Greg KJ6ER. And I made a video about this specific antenna called, he calls it the Marauder. He always has really really interesting names for his antennas. But essentially, what it is two vertical whips with horizontal wires,
Okay.
and they have I used basically lawn trimming line to insulate the reflector from the director. And the horizontal wires have different sections for different bands. So you adjust the whips and you adjust the horizontal wires and you tune it for a monoband antenna for each band.
That makes sense. Thank you
Yep.
so much. Again, great presentation.
Thank you. I appreciate that.
Okay, let me get this gentleman real quick.
Hi, right before you mentioned the reverse beacon network, you mentioned there was another system and way of doing it. I didn't quite catch that. Can you tell me what that is? How you use
Yeah, so there's a method of using the Kiwi SDR. And so I don't know if you've logged into it's basically an SDR website. You can log into stations all over the world. And uh, like I said, it's a little time consuming to find a station that can hear you and has a low noise level. But I do this to basically do direct comparisons from, you know, uh, different antennas. So you can have an antenna switch, uh, log into a Kiwi SDR, pull up their S meter attachment, which will give you a very nice chart, and key up your radio. I just used a carrier tone on CW, a straight key or something, and it'll give you, S5, S6, switch antennas, and then I'll give you another. And what's interesting, if you have a directional antenna, you can actually use that to create a azimuth map or an azimuth plot of the gain of your antenna, front to back. And there was a really great YouTube video. I forget it's called VE6. I forgot his call sign. He has a wonderful video on that I can forward to anybody that's interested. That's where I got the idea. And I've used that for a couple of my videos comparing different antennas. It works really well.
Okay, right here. Gotcha.
All right, well, thanks for your presentation. Very nicely done. I remember at one point you discussing, if I remember correctly, a vertical radiating element with a sloping counterpoise or something close to that. Could you revisit that perhaps and maybe elaborate?
Yeah, so the vertical infant half wave is basically just using a vertical half wave radiating element, and then the counterpoise just slopes down. I didn't mention this in my presentation. That is not a true omnidirectional radiation pattern. It's actually skewed slightly in the direction of the counterpoise, according to my models anyway. But we're not talking much. We're talking less than a dB. But you do get a slight skew of that radiation pattern towards the counterpoise. But yeah, essentially that's just a vertical half wave that I use a whip a lot of times. And you can basically just adjust the length of the whip to be resonant on whatever band you're going to operate.
Oh, okay. Over there.
Thank you for the wonderful presentation. It's rare that anyone presents the experimental results of what they've done. It's all simulations or number of contacts, so I appreciate that. A comment and a question. Comment is, so internet receivers are great ways to test antennas. So is the RBN and so is Whisper. So there are three great.
Whisper's great, yeah.
And you don't need to know CW to use an RBN.
Yeah.
Put it in the message key, or all you need is CQ in your call.
That's one suggestion I would say is if you don't know CW, you can still use reverse beacon network. You can send test your call sign, but Whisper's another great. I haven't messed with Whisper much. I have a buddy that's a big time POTA guy. He has Whisper running 24/7 at his house, and so when he gets to the park, he knows what bands are open. It's a great resource. I've been meaning to get into that. I just haven't gotten into that yet. So really great resource as well.
Those are super tools. Last is a question that's really for the group and not for you, Tim. How many people, I use the NFED half wave. I think they're terrific. How many other people use these? Maybe 7 people or so raised their
It's a very popular antenna. I'm amazed sometimes. I was doing that SOTA activation on Tuesday, running 5 watts for my KX2, and I couldn't believe the amount of contacts I got. And a lot of DX too. It's a fantastic antenna, especially a lot of people. There's one guy that has a YouTube channel that his whole channel is basically saying how terrible an infrared half wave is. But I think it is a great antenna. You do have to understand there is loss associated with the transformer, but you have loss with a lot of things in our hobby. So I think it's a wonderful antenna, and you can really utilize it and make a lot of really good contacts.
Okay, I think we have some questions on Zoom. Ben, why don't you go ahead and coordinate that, and let's get those questions answered.
Okay, I have I think 3 on Zoom, and 2 of them are me. So, so that makes it easy. First, thank you for the presentation. In particular, that the slide where you overlaid the waves, the red and the blue one.
Oh yeah,
that was a really nice slide, and I think it's makes this topic really accessible. Okay, the first question I have related to your transformer heat loss slide, where you noticed you had really terrible loss.
Yeah.
Did you see that loss as the radio cranking itself down because of reflections, or just the heat in the transformer, or both?
So there was a lot happening in that activation, and this was when I was first starting to learn about antennas. But essentially, I was doing a activation, and I noticed my SWR would start to climb, and I would stop transmitting, it would come back down, and so essentially that transformer was starting to fail on me. It had so much heat built up. And like I said, when I went out there, that that toroid was melting through the 3D printed enclosure. Now that was a 1010's transformer, and I believe he uses a FT240-43 with a twisted winding, a twisted primary. So I haven't had any issues like that with my new transformer with that thick toroid. I think if you're going to use this antenna, you might look at building one of those. Um, Much more efficient. I can run 100 watts on that all day. It doesn't even get warm. I was shocked by that.
So do you think it's more like a thermal behavior, as in the resistance changes as the temperature goes up, or do you think it's about the material or some combination?
I wish I could answer that. I'm not going to pretend to explain it. I know it works. Colin MM0OPX has a lot of videos on that specific toroid, and he may answer that a little bit better. I'm not an engineer. I know that there's a lot going on in that toroid. You have a lot of reactants. There's a lot of stuff going on. I know that the thicker toroids tend to work better, and according to the nano VNA test, are supposedly more efficient.
Okay, thank you. And then the
Mhm.
next one was, in my personal experience, I use NFED half waves sometimes, but I more often use NFED random
Yeah,
wires.
yeah.
And with both of them, I noticed that I get much better performance if my counterpoise is literally touching the ground. It doesn't matter as much how long it is, as long as I
Uh-huh.
literally get it onto the ground. And I wanted to ask you, is there any science behind that, or is that just
You
correlation?
know, so that's really interesting because I've seen a lot of different thoughts and opinions on this, and I don't know if I can answer this scientifically. But there is something that happens when counterpoise on the ground. It can couple with the ground. Now, what I've noticed is sometimes that will help an SWR lower. For example, I built a off-center fed vertical that I use a lot called a Challenger, and I noticed that when I raise the antenna up higher and the short counterpoise is not touching the ground, my SWR is not as low. Now, when I drop it to the ground, I get a much better SWR. Is the antenna any more efficient? I don't know. Um, Typically speaking, especially with quarter wave verticals, elevated radials tend to be more efficient. And I believe with non-resonant antennas, that is the case too. I have heard a lot of people talking about. I used a 29-foot random wire extensively last year, and I would just use one 17-foot counterpoise. But now I'm reading that elevating the feed point and using elevated radials may actually help out and have lower loss. So I think there are different thoughts on that. You may ask 10 people and get 10 different answers. But I saw a presentation recently on the Super Rybakov. It's a 43-foot non-resonant antenna. And this guy had a really nice presentation, and he tried to limit all the losses. So he put the matching unit, basically a remote tuner at the feed point to reduce any kind of loss, because anytime you have high SWR on the feed line, you're going to have loss. And then he also has elevated radials to decrease loss. So I think, in my opinion, elevated radials tend to have lower loss, but you may get better coupling with the earth with a counterpoise on the ground. So I think there's a lot of different opinions, and I don't know if I can really answer your question.
Sure, thanks. Sometimes you ask 10 people and get 12 answers.
Yeah.
The last question from the Zoom is, so the optimal counterpoise for a 40-meter, 66-foot primary radiator would be about 6 feet or 10%? Question mark.
Yeah, so 5% of a wavelength on the lowest frequency you're going to use. On 40 meters, that's approximately 6.5 feet. I have to do the math, but approximately 2 meters. So I don't know if there's any benefit with more of a counterpoise. From my understanding, there's not. I've read other people, some people suggest putting a bunch of radials on their infed half wave. I don't know if there's any benefit. I haven't seen any benefit to that.
Thank you.
Okay, Joe's got a question, Elliot, and then this gentleman. You got to wait, Andy. I got a line going here.
Yeah, you had mentioned that I'm Joe WB6 JOE. You had mentioned that one of your favorite antennas is the doublet. If I got 33 to throw something in the air, I'm using the inverted V doublet before I'm going to use a inverted or a NPET.
Yeah, I agree. In my opinion, the doublet is probably the king of multi-band simple wire antennas. And I have had some really wonderful activations. In fact, Monday night I was camping out about 7,000 feet with the doublet up 30 feet, and it was an incredible experience. A lot of really nice contacts and DX with the doublet. You got a highly efficient antenna on multiple bands, ladder line. There's nothing to not love about a doublet.
Okay. Elliot, you had okay, Elliot, then him. Elliot's got a new call sign too. You got to tell us.
And Elliot, K9EO. Yeah, so I have a question that I've had actually for quite a while, and since you have a lot of knowledge about unfed half waves, I'm curious if you know the answer because I've gotten some conflicting information about it. I know that because of fewer interactions with the ground, the part of the antenna that is further up is going to actually have better radiation, more actual radiation, and you can see
Yep.
that in the charts that you
Yep.
show. But is
Sure.
the azimuthal direction of that radiation concentrated up the wire or broadside, which would actually be back down the wire in approximate?
So I think I understand what you're asking. So first of all, as far as the typically speaking with antennas, you want the high current point of the antenna to be high off the ground. And with any antennas, and I actually had a buddy email me recently. He was he's a big into kites, and he wants to put an infed half wave up on a kite. And so I modeled it for him. I was just kind of curious myself. Anytime you start putting these antennas higher and higher, now you're starting to really change your radiation patterns. Often you'll get much lower takeoff angles and more gain. So that tends to make the antenna a lot better. Now, I'm not sure if I quite understood as far as what you said about the radiation coming down the wire. Um, the radiation patterns I showed, there is some gain to the back of the antenna with some of the different configurations. I kind of highlighted the lobes with the most gain. I didn't really show you in my videos. I kind of spent way too much time going over every little bit, but I wanted to kind of give you the highlights.
Yeah, so maybe to clarify my question a little bit, let's imagine that you have a sloper configuration where the feed point is at the south end of the antenna, and then the highest elevation is at the north end, and
Yep.
you're using it on one of the higher bands where you've got those two lobes.
Those lobes, yeah.
Are those going to be at 45 and 315, or are they going to be at 135 and 205 or whatever?
Okay, yes, I see what you're saying. So yeah, you those lobes are those main lobes on the sloper on 15 to 10 meters are about 40 to 45 degrees off the end of the wire, wherever that's pointed. You do get a little bit of gain off the back end of the antenna, but those are the primary lobes. So if I was trying to get DX, I would point that antenna right between the spots I would want to get. So like for me, if I point that directly north, 45 degrees gets me into Europe and then Asia on the other side.
Hi, I'm George K and 6QZY, and thanks very much for your presentation. It's fantastic.
Thank you.
The question I have has to do with the support pole. If you have a support pole that's metallic,
Yeah.
have you studied the effect of that? And can you provide us with any pointers? For example, say I'm doing a sloper and I happen to have a metallic support pole the other end. Is that a bad thing?
What I would say is, yeah, I think that there is going to be some kind of coupling effect, and it could be a bad thing. But what I would say is, especially for me doing portable operations, there's no perfect deployment of an antenna. There's always going to be compromises. A lot of times I'll use a antenna right by my truck, which is going to couple and have some effect. Maybe it's going to help act as some kind of reflector and help my signal. I don't know. What I would say is trying to get the antenna as far away from the metal as you can is going to be helpful. But if you walk out to the side of my house right now, my infed half wave is just a few inches away from the metal pole secure. It's an inverted L. So it's not ideal. I have it going, so it's the portion close to the wire, the portion close to the pole is only a few inches of the wire. So I try to minimize that, but it's not ideal, but it works fine. It's still going to work, but you may have some negative effects. But I'm not sure exactly how to experiment or test that.
The question was, have you tried modeling that?
I don't know exactly how to model that as far as any metal objects. I'm still fairly new to antenna modeling. I can model the basic antennas, but as far as like putting metallic objects, I'm not even sure if you can do that. But maybe I'll look into that.
I wonder if your program models a skydiver 10,000 feet in the air.
I'm really curious about what kind of antenna he's going to use HF, because that's going to get out pretty well regardless of what he
been an
uses.
end-fed.
End-fed, yeah.
Okay.
When I modeled my buddy's kite antenna, it was actually very interesting. Very, very low takeoff angles and a lot of gain compared to closer to the ground.
Yeah, so as everyone's been mentioning, good presentation. I'm Aiden, KO6 EJM, and I was wondering what kind of wire you would use for the transformers.
Uh-huh.
Be just your regular rubber insulated, or would that be something else?
I tend to use magnet wire. I think that's what most people use for the transformers. I think you can use other type of wires. There's different sizes of magnet wire, so depending on how much power. But I think like 18 gauge magnet wire should be fine for 100 watts. If you're wanting to build one of these for a full legal limit, you're going to have to stack a few Torahs together and use 16, 14 gauge wire. But for 100 watts, I prefer 18 gauge magnet wire or 16 gauge, whatever you've got on hand. Seems to work well. But you can use other wire, and other people do use other wire, but I'm not really sure if that's going to affect anything.
All right, yeah, thank you.
You're welcome.
Okay. Oh, Andy's got another question.
Yeah. Hey, you know how in power transformers, they use these E-shaped sheets that interleave, and that prevents hysteresis and a lot of loss in transformers. Hasn't anybody tried to make something like that work at HF?
I am not familiar with that. I will have to research that. I really don't know. That's interesting. You'd have to clarify exactly. I'm not even sure exactly what you're talking about, quite frankly. You said the H. I might have to write that down.
I think we have another person that might have input there.
This is Kit WA6PWW using laminated steel E-cores like you find in a power transformer does not work at HF.
Oh, okay. Okay.
Far, far too high. It would
I got you.
Make a really good heater, actually. Which is what's happening to your core when it was getting hot.
Yep.
To the question a little earlier, was it thermal losses? Yes.
Definitely.
It was changing, and the core characteristics were changing.
Definitely.
And I've done this stuff for several decades. So.
Yep. Yep.
Basically, thermal effects at that point become a problem. That's why the larger core works better.
And I believe once that core gets saturated with heat, it no longer is doing the impedance transformation. That's why I saw my SWR start to climb.
Yeah, the Curie point for ferrite that you're using is about 450 Celsius.
Yeah.
If it gets that hot, you've got other problems.
Go ahead, Connie.
Follow up to that question. So laminated steel E-cores aren't going to work. I think we could have predicted that. But what if, could you use another material other than steel? Use some kind of ferrite material. There's all sorts of different mixes and materials.
Well, that's what he is using is a ferrite. It's
I
a
see.
43 ferrite from the part number he had.
No, I'm not talking about him. I'm talking about some kind of laminated core.
Ferrite, by the way it's put together, technically is a laminated core. It's little bits of iron isolated in a ceramic matrix.
Okay.
So it's not solid metal.
Well, no, I'm not. I'm talking about the lamination. So that's really good information. I think I've got some homework to do.
Ferrite or powdered iron are basically little bits of iron isolated in a ceramic matrix.
Okay, excellent. Thank you.
Okay, and Tim, maybe you can solve the question that comes up. Do you really have to etch off the enamel, or does it burn when you solder it?
Okay. So, I typically on the larger magnet wire, I tend to scrape it and burn it. I try everything. What I've noticed on the smaller, I just built a little QRP radio and had to wind a bunch of toroids. Soldering worked great for that really small magnet wire, and it tins it at the same time. But on the larger magnet wire, I tend to use a razor blade and scrape it, and then use a soldering iron. So I kind of want to make sure I get it all off. But
Yeah, I learned that Klein Tool has a device that is actually manufactured to do that.
I will have to look that up because if the amount of antennas I build, I might use that.
Okay, another question here.
There's two types of magnet wire coating. One's called polythermalase, which melts and evaporates when you heat it with a soldering iron. And that one you can do it. The other, the older style magnet wire enamel coating, you can heat it until the house burns down and it won't come off. So you got to scrape that.
Scrape it off. Yeah.
So it's best just to scrape it off. Anybody
Yeah.
on Zoom? Question on Zoom? Because we're going to have to wrap this up soon. Any more in the room got questions? Hey, by the way, everybody, Tim is mentioning Greg's name, KJ6ER. And guess what? He's going to be here in June. So we may have
that's
part
great.
2 on antennas here. Hope you don't get too overwhelmed by antennas, but man, this guy is really good too with antennas. He kind of has another twist to it, and he's local, so I believe he'll be showing up in person. So stay tuned for that one.
Yeah, you need to check out. Greg become a good friend. In fact, he's called me and run a lot of his new antennas by me, and he did a presentation for our ham radio club, and it was fantastic. He is a very knowledgeable guy, really good presenter too.
All righty, everybody. Anybody last go for questions for Tim? Oh, yeah, you're welcome to join in as well on Zoom, because you just go to our Para website and you'll see the link in our website. But very good. All right, Tim. Well, gosh, this has been great. I just feel so honored to have you here.
Thank you. I really appreciate it. It's been a lot of fun.
Come back anytime, Tim. We'd like to see you.
Yeah, the whole room's clapping here for you.